Hello everyone, I'm Avrila at Math with Avrila, and I'm here today to show you a calculus proof for the vertex of a parabola. So we're given some formula, f of x, some parabola, and we're saying that it's quadratic. So yeah, quadratic parabola, that's how that goes. Let's see, f of x, so we've just got some function. And we're being asked to prove the formula for the vertex of that function. So what a lot of people will say is, okay, we know it's a parabola, so it looks something like this or something like this, but either way it's got its two solutions, its axis of symmetry and its vertex. Similarly, it's got its two solutions, its axis of symmetry, and its vertex. Okay, well, we know something about those two solutions. So, because it's quadratic, we know that f of x is ax squared plus bx plus c for some real numbers a, b, and c. Now, what we want to find out is those solutions. Well, we've got a formula for that. So the x values at those two roots of the parabola will be negative b plus or minus. So usually this one's the plus, that one's the minus. The square root of b squared minus 4ac over 2a. You notice there's two of them. Like I said, not a coincidence. Okay, so if we want to know halfway between them, what we would do there is use symmetry and say, okay, we're finding the midpoint of those two values. So that midpoint, just in the x's, we'll just calculate from that. Well, that midpoint is going to be these two things added together. So negative b plus that square root of b squared minus 4ac. Now, if we were just doing this on a particular parabola, we would probably plug in those numbers, but we're trying to prove the formula in general. So we want to leave everything as letters as much as we can. And then to find that midpoint, we need to also add on the minus version, so the other solution. And then split that down the middle. So divide it by 2. Okay, this seems like a lot. Now, that's not a coincidence that this seems like a lot, actually. So let's see what we can do to tidy this up. Well, we know that that's just all going to be over one big common denominator, and we can move the 2a into the other denominator. If that's confusing, review some fraction calculations. I'm just going to ask you to either trust me or ask me about it later. And then I notice that we've got a couple of like terms here, plus and minus that same radical. So what I see here is we have negative 2b over 4a, which simplifies in a fairly tiny matter to negative b over 2a. Okay, so we know that x value is negative b over 2a. And then we can just evaluate that particular x value. So plug that value into the function and see what that comes out to be. So the coordinates of that vertex are going to be told to you by that. Now, we made a couple of assumptions here. First of all, we assumed that those two solutions actually exist. Now, it's true that this still works if this radicand is negative, because they're just imaginary, but we can't really see from this picture why that has to be true. We just know that it does work. And then another thing is, in this problem statement, we were told to use calculus. Well, we didn't really use any calculus anywhere in here. We just used a bunch of algebra. we want to use calculus for this. So in calculus, the way we deal with trying to find that vertex would be, we would notice, well, that's a maximum. So here's what we know. Starting over again from what we know, that parabola has to follow the formula ax squared plus bx plus c. Well, that means the derivative, and here we're using that calculus, is going to follow the formula 2ax plus b. Again, for serious calculus reasons, if you want to know about them, I'll be happy to make another video for it. For the moment, I'm just going to ask you to trust me on this. Feel free to verify. Okay, well, we can see that that maximum or minimum, whichever, is where a tangent line sort of sketched across, instead of like one here that would be going up or one here that would be going back down, this point right here is exactly where that tangent line sort of tips from increasing to decreasing, and that is where that tangent line is like a constant, so it has a slope of 0. Well, that derivative tells us the slope of the tangent line. So let's see when that derivative is equal to 0. Well, remember we want to solve for x, so I'm going to start by adding b on both sides. So now we're using algebra again, but that's okay because we already used calculus here. And we used things we know about derivatives, which is more calculus, to set up this equation. It's often true that you need some algebra to efficiently use something that you've set up using calculus. So now I see that 2ax equals negative b. Well, what I want to know is x, so I'm going to divide off that 2a. And now I see that it's very tidy and very easy to prove. In fact, we didn't have to do a lot of complicated stuff. It's very easy to see that where the parabola turns from either increasing to decreasing or decreasing to increasing, that value of x is negative b over 2a. And we can find the value of the function at that point, so the y-coordinate, by just doing f of whatever we get from that. And so now we have a proof for that using calculus. And you might notice that compared to just all the stuff that went into this, all the complicated algebra that we use, and it would have been even worse if we hadn't noticed that those cancel nicely, and we had to do fraction stuff. No one ever likes fraction stuff, right? You might tolerate it as a means to an end, but I don't think it's most people's favorite thing. Well, the calculus proof, or the proof using calculus, was very short, really. We just started from what we were given, took a derivative, set that derivative equal to 0, did a little bit of algebra to solve it, and then just said, okay, common sense, if we know the x value, we can calculate the y value using the original formula. So a very short, simple proof of a fact that was tricky to prove without calculus. So this is a thing that pretty often happens in math. Even if you can show something by an easier method, it's often or by like a previous method, like this is where we get into the difference between simple and easy. Calculus has a lot of moving parts to make it work, but once it's up and running, a lot of things are really straightforward with it. With algebra, with just algebra, or what would really be terrible, just arithmetic, having to do this all with only individual numbers, not finding patterns to help us out with the next one. With those, this would have been a much longer proof even than the algebra version of it. So it's like if all you have is a hammer, everything looks like a nail. Well, if you have a little more than a hammer, like a screwdriver, you can still do a lot of the same things. You know, nails and screws do the same job, but the screwdriver and the screws are just a little more efficient depending on what you're trying to do, and sometimes getting a little bit of leverage, which actually a screw is one long wrapped around lever, that can help you out a lot. So drop some questions and let's see what you come up with, trying out some math on other things. And for now, I will calc you later.